Hello. This lecture will cover pages 85 through 86 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Operational Amplifiers, Chapter 4H, the Instrumentation Amplifier. One of the most popular configurations of the operational amplifier is to use it in what they call an instrumentation amplifier configuration. And we're going to be on page 85 and we're going to analyze a circuit. The instrumentation amplifier is shown below, and that's this circuit right here. These amplifiers are widely used in many industrial measurement, data acquisition, and medical applications where DC precision and gain accuracy must be maintained within a noisy environment, and where large common mode signals, usually at the AC power line frequency, are present. What I'm going to do is we're going to analyze this particular instrumentation amplifier, and in the process determine the voltage at V1, the voltage at V2, the voltage at V3, and the voltage V out for two different input voltages. So if you take a look here, part A says we want to find V1, V2, V3, and V out when VA is equal to 2 volts and VB is equal to 2 volts. Let's go through this and see how we would analyze that particular circuit. I want you to follow me very carefully because I'm going to have you do this in just a minute. The first thing we're going to do is we're going to put a 2 volt signal, right? A 2 volt voltage level right there, and we're going to put a 2 volt voltage level right here. And I want you to notice that the operational amplifier will try to maintain these voltage so we can project this voltage to this point, which is 2 volts right there, same point. And we can project this 2 volts back over to the negative, the inverting terminal here of this bottom operational amplifier, and that'll put 2 volts right here. I want you to notice that if there's 2 volts on this side of this resistor and 2 volts on this side of the resistor, there's no current flowing through that resistor. We know that this current right here is 0, ideally. So if there's no current flowing through this resistor, and there's no current flowing in this direction, there can't be any current flowing in any direction through this 4K resistor. So if there's 2 volts right here and there's no voltage drop across this resistor, V1 has to be equal to 2 volts. So in this case, V1 is equal to 2 volts. If V1 is 2 volts, the voltage at V2, this is just a voltage divider. You might say, well, what about this part of the circuit? It's very high resistance. No current can flow through here, so that's just a big infinite resistor, obviously, right here. So we can forget about that. And if there's 2 volts right here and these resistors are equal, the voltage divider rule tells us that 2 volts times 4 divided by 8, that puts 1 volt at this point. So now we know that V1 is 2 volts and V2 is 1 volt. If you have 2 volts here, there's no current, and there's 2 volts here, there's no current through this resistor still, and there's no current here. That means there's no current in this particular element, no voltage drop, which puts 2 volts down here. Now what I'm going to do is I'm going to I have 1 volt placed at this point, and I have 2 volts placed at this point. I'm just going to take a look at this circuit right here, and I'm going to analyze it using the superposition technique. I'm going to start out by taking this 1 volt up here and grounding this point here. And if you take a look at that, that's a configuration we're familiar with. It's a non-inverting amplifier where the gain from this point right here on the V plus input is 4K over 4K plus 1. So it's a gain of 2. So if you have 1 volt here and you have a gain of positive 2 to this point, that gives us an output voltage right here of plus 2 volts. But that's only part of the solution, because now we have to basically ground this point up here, and we have to see what this 2 volts down here is going to give us. Well, if you take a look at this circuit with this point here being ground, we know that's a inverting amplifier, and its gain is this feedback is negative, this feedback resistor divided by this point, so it's a -1. There's a gain of -1 from this point. This is just a inverting amplifier circuit at that point. 2 times a -1 is a -2. You add those up, and your output V out is 0 volts. There's V1. V1 is 2 volts. There's V2. V2 is 1 volt. There's V3. V3 is 2 volts. And down here's your V out. V out is 0 volts. And that's how you analyze that circuit. What I'd like you to do is I'd like you to do B on your own now. Keep it in mind that VA is going to be 4 volts. VB is going to be 0 volts. And I want you to take your time and go through and see if you can find V1, V2, V3, and V out for this circuit. Stop the video and just try that for a minute, and then you can turn it back on and let me analyze it for you and see if you can follow along. Hopefully you did it this way. If you have 4 volts here and you can project that to this point, that gives us 4 volts at that point. If you have 0 volts here, you can always project it over here for the reasons we discussed, and that gives you 0 volts. That makes this a positive with respect to this side. If you have 4 volts across 4 k ohms, that gives you 1 milliamp flowing in that direction. You have 1 milliamp of current in that circuit flowing from this point to this point. You don't have to do Kirchhoff's current law at that node. Basically, there's no current in this branch right here because that's an infinite resistance. You know that. We always let that go to 0. So that current has to be coming from here, from this output V1, plus to minus. So if 1 milliamp is flowing through that 4 k ohm resistor plus to minus, that's a 4 volt drop there, from minus to plus. So if you have 4 volts here and you come up another 4 volts, V1 equal 8 volts. There's your V1. Using the voltage divider rule, which we talked about a minute ago in the previous problem, this is just a high input resistance here. 8 times 4 divided by 8, that leaves you V2 as 4 volts. Now we calculated V1, we calculated V2. Let's get out here and see if we can't get V3. If you have 4 milliamps flowing down here for the reasons we discussed, none of the current goes here. All the current goes through here, plus to minus. If you have 1 milliamp flowing through 4 k ohms, that's 4 volts. If this is 0 volts and it's plus to minus, that leaves V3 at a minus 4 volts. Now what we're going to do is we're going to use superposition on this last amplifier right here, and we're going to determine what V out is, but we have 2 calculations to make. The first thing I'm going to do is ground this point, and I'm going to recognize that this 4 volts on that V plus input is just a non-inverting input with a gain here of 1 plus 4k over 4k, or a gain of 2. So 4 times a plus 2 gives you V out here at plus 8 volts. But that's only part of the solution because it's just with this. Now we have to ground this point, come back down to here, and V3 is at a minus 4 volts. This is an inverting amplifier circuit. Its gain is a minus 1. It's a minus 4k, the feedback resistor, over 4k. That's a minus 1. A minus 1 times a minus 4 volts gives you an output of plus 4 volts. Algebraically, you add those up, you get 12 volts for V out. We calculated V1 of 8 volts. We calculated V2 of 4 volts. We calculated V3 of minus 4 volts. And we calculated V out of 12 volts. Hopefully you did it that way. Well, what I'd like you to do, if you look at page number 86, is I'd like you to go ahead, and I didn't give you the individual voltages on page 86 like I did here, but Let's let VA equal 2 volts and let VB equal 0 volts. See if you can calculate an output of 6 volts. I didn't show you the intermediate voltages like I did on A and B, but with letting VA equal 2 volts and VB equal 0 volts, let's see if you can go ahead and calculate V out equal to a plus 6 volts. When you do that, what I want you to do is, based on all those calculations for A and calculations for B and then calculations for the extra analysis that I gave you, based on those calculations, what relationship, if any, can be said about V out with respect to VA and VB? Well, if you take a look at, in all cases, it turns out that the output voltage is always VA minus VB times a gain of 3. That's the relationship. Take VA, subtract VB, take that quantity times 3, and you always get V out. The big thing to see here in this instrumentation amplifier is that it's a difference amplifier times a gain of some sort. Now, why we said that is so popular in many industrial measurement, data acquisition, and medical applications is because if you have any noise, we talked about noise up here, but if you have any noise riding on this, and you'll have noise, white noise, you'll have white noise riding on this, or 60 hertz electromagnetic interference. Notice that this wire and this wire is in proximity to one another. So if you're jumping up here with the voltage, call that plus V noise. And you're jumping up here with the voltage, let's call that plus V noise. Do you understand that this instrumentation takes the difference of those voltages? And if they're equal, their net effect will be 0. Think about that. If you have 4 volts, let's say you have, for a certain period of time, you have 4 volts on VA. It jumps up to 4 volts like that. That jumps up to 4 volts. And you have all this noise here, and here, and here. Down here, let's say that stays at 0 volts. Let's say this is staying at 0 volts down here on VB. The same noise that you have riding on this wire here, you're going to have that same noise riding on this wire. The only thing that gets amplified here is the difference, which is basically going to be the 4 minus the 0 times a gain, because this noise is common. You'll hear that in future courses called common mode rejection. Common mode rejection. That's why instrumentation amplifiers are so popular. That concludes this brief lecture on instrumentation amplifiers.